Greetings from across the Atlantic Ocean and the Mediterranean Sea. I'm Hauke Schulz, and I'm happy to introduce Ayub Fatihi on behalf of the entire mentor team. Ayub took on the challenge number 12, compressing geospatial data with varying information density. In just a second, he will introduce this subject to you and what that long title actually means. But let me back up a little bit and tell us a bit about ourselves and how this project came about. So we understand that this project is not only a Code for Earth project, but actually also kind of an Earth for Code project, since we are spread over 3 continents, 4 time zones, and up to 8 hours apart. So Ayub Fatihi, our mentee, is joining from Morocco. From the mentor team, Milan Klöver is joining from the MIT at the US East Coast. Juan Jose Dominguez and Miha Ratzinger from the ECMWF in the UK, and myself joining from the West Coast of the US, the University of Washington. What I really like about this project is how it came along. So, as you might know, we produce more and more data as a society, and climate science is really no exception to it. We always push the envelope and create more and more data, especially with going to higher and higher resolution with our climate simulations. Doing climate simulations myself, I figured that I need a better compression algorithm. Normal, lossless compression algorithms like zip were not up to the task. I needed something more rigorous, something that compresses my data more, and that can only be achieved by lossy compressions. Something like MP4 for music, I needed for climate simulations. Then, while doing some literature research, I came across Milan Klöver's work, and he did a fantastic job in a previous Code for Earth project, where he developed an algorithm that kind of decides what is information in a 2D field and what is not information, what is noise, what can be basically thrown away and doesn't affect the analysis afterwards. So doesn't affect the mean, doesn't affect the gradient of some fields. Basically is similar to throwing away high tones in an MP3 file that the human ear can't hear anyway. So with this being said, I was happy that Milan's algorithm was open source and I could immediately test his algorithm on my own data sets. Connecting then through GitHub with him, we then developed further ideas, and with a colleague of mine, I wrapped his code in my preferred programming language, Python, and that's how we ended up hosting the challenge here for Code for Earth after we developed additional ideas how to even further compress climate simulations, or actually any n-dimensional field, really. So by partnering with Code for Earth, these ideas became to life, especially thanks to our mentee, Ayub Fatihi. So for me, this is really a nice success story of open source, and hopefully it encouraged more people to publish and collaborate in the open. But without further ado, please enjoy Ayub's presentation, bringing our ideas to life. Thank you.
Greetings. Thank you for joining me today. I am Ayub. In this year's Code for Earth edition, my focus is on compressing geospatial data with varying information density. I'm grateful for the guidance and supervision provided by Hauke, Milan, Juan and Miha throughout the course of this project. The exponential growth of data across multiple fields has created a demand for efficient data management. According to ECMWF, An astonishing 300 terabytes of atmospheric data are being added to the data archive on a daily basis. Also, according to the ECMWF, its data archive is rapidly approaching the exabyte mark. The pressing question is, with this exponential growth, where will the data archive stand in just a few years? Will it enter the Google regime? And furthermore, the graph underscores the critical role of compression. The green dots on the graph represent 10x and 100x compression. So, what is compression? Data compression, also known as source coding or bitrate reduction, relates to encoding information using fewer bits than the original representation. It offers several advantages, including saving storage space, reducing bandwidth requirements, and improving overall system performance. Data compression involves a trade-off between precision, size, and compression-decompression speeds. Concerning the precision, it is different than the information content. One example would be someone measuring temperature in his backyard at 6 or 7 or more decimals. It is very precise, but not enough information to get the temperature across the whole city. The goal is to achieve optimal results in all aspects. However, in practice, the aim is to strike a balance that suits the requirements of the application and the available resources. Before getting any further, I want to remind you of how floating numbers are stored in memory. It is actually similar to scientific notation, but in base 2. So the first bit is reserved for the sign. If it is 0, the number is positive. If it is 1, as in this example, the number is negative. The next set of bits represent the biased exponent. It controls how far and in which direction to move the decimal point in the fraction. The bias is a function of number of bits reserved for the exponent. The bias is then subtracted from the calculated exponent to get the biased exponent value, 4 in this case. The remaining bits represent the mantissa, also known as the significand or fraction. These bits represent the fractional portion of the number in binary form. The bitwise real information content-based compression is done as follows. The bitwise information, that is the mutual information between the bits, is calculated. A bit position contains more real information, the stronger the statistical dependence to the adjacent bit is. Then we keep only the bits with real information and discarding the bits with false information. After that, we apply our lossless compression. Before delving into how this compression is implemented, in this plot presented in Clover and Alt's paper, we visualize the compression of water vapor data from the CAMS dataset along the longitudinal dimension. We observe the transition from preserving 100% of information on the left to 83 on the right. The purpose of this demonstration is to showcase the impact of compression, as depicted in the right-hand side. The visual representation appears very pixelated and we start losing data. However, it highlights that you can easily preserve around 100% or 99% of information without sacrificing any crucial details within the dataset. But if we give a closer look to the cartoon land in the right side, near the poles, it is actually not that bad. And this is the motivation to explore adaptive compression on chunks as a challenge for this year. So back to the bitwise real information content-based compression. So we will go through it step by step. So we assume working with graded data from Cartesian curvilinear or unstructured grids and utilize a binary representation for efficient storage. Then we analyze the mutual information of adjacent bit positions. As an example, let's focus on the sign bit and examine the spatial distribution of all sign bits. When we look at one bit, we inquire about its significance in relation to its neighboring bits, and thus we have more mutual information if the bits have something in common, and less mutual information if the bits just appear randomly. And we do that for the other bits, the exponent bits and mantissa bits, to identify the key bits, which are the significant bits that preserve over 99% of real information or any other wanted percentage. Finally, we remove the false information bits by rounding them to 0, ensuring effective compression without substantial data loss. In this example, we start with a one-dimensional bit stream of data. Using the concept of mutual information, we identify and retain only the significant bits, and the compression can be thought of something like this. And by applying this approach, we compress the data from 160 bits to just 60 bits. To illustrate the bitwise real information context-based compression, I will share an example with code. For this, we will be using xbitinfo, which is an X-array wrapper around the bit information GL, to retrieve and apply the bit rounding from within Python. The package intends to present an easy pipeline to compress climate datasets based on the real information content. The xbitinfo package is mainly developed and maintained by Hauke Schulz and Aaron Spring. And for bit information GL, it was developed during the summer code editions of the years 2020 and 2021 by Milan Klöver. The dataset used for this example is the 2-meter temperature in Kelvin from the ERA 5 dataset, and the data type used is float 32. And you can get this data from the Copernicus climate data store. So first thing is getting the information content per bit. For that, we use the get bit information function that calculates the information content for each bit, the sign bit and the exponent bits and the mantissa bits. And as we can see, the first bits contain no real information. Then the values start relatively high and start decreasing near the end. The second step is to discard bits without real information. And to do that, we have to define our key bits that are the number of bits from the mantissa that are necessary to retain approximately 99% of the information or any other percentage we want. In this particular case, the key bits value is calculated to 8 bits. This value is then utilized to round the original data using the XR bit round function. The third step is doing the lossless compression. In this slide, the original size is of 64 megabytes, which can typically be compressed to approximately 34 megabytes, resulting in a compression ratio of 2. However, when compression the bit rounded data, it results of a size of 4.1 megabytes, achieving an impressive compression ratio of approximately 15. So the challenge I have been working on this month is a continuity of the compression method using bitwise real information content that has been developed during last editions of 2020 and 2021 by Milan Klöver. And this year I am working on the development of an information density adapting compression by implementing compression and bit information retrieval on a chunk basis, and analyzing the information density of climate variables across space, and studying the optimal chunk size depending on specific features like hurricanes. So we have examined the impact of chunking on hurricanes. Using the ERA 5 data, we analyzed the Dorian hurricane, like in this case for wind speed variable. and we did not observe any significant differences in the variance of Kippett's value for the chunk where the hurricane occurred. Similar findings can be observed also for the Dorian hurricane using the mean sea level pressure variable. Next, we applied chunking across latitude and longitude on multiple climate datasets. First, we have direct solar radiation. In this plot, we observe the variation in values across latitude and longitude, with high values in Antarctica and null values in the Arctic. And when applying bit rounding to the entire dataset, it employs a total of 12 key bits for keeping 99% of the information. By utilizing chunking, we observe a spectrum of key bits value varying from 0 in some chunks, like in the Arctic, to a maximum of 15 in other chunks. Regarding the disk storage utilization for the compression of bit-rounded chunks, it is noteworthy that it has accomplished a storage saving of 59 megabytes compared to the dataset bit-rounded and compressed as a whole. This efficiency is further amplified by the fact that we are retaining higher precision where it is most crucial. Among the other variables we examined, there is convective precipitation. In this plot, value disparities are apparent across latitude and longitude. And the bit rounding across the complete dataset involves utilizing 8 key bits to maintain 99% of the information. Chunking reveals a diverse range of key bits values, with some chunks containing no key bits at all, like in the Antarctica, while others stored as many as 12 key bits. This diversity in key bits value underscores the precision with which data is captured through chunking in certain regions. Compression the bit-rounded chunks gives similar results as compression the dataset as a whole, and the chunking strategy proves advantageous by preserving higher precision where it's mostly needed. And we tried to apply chunking on multi-level datasets. In this plot, we are exploring one variable, namely the specific humidity, but at different vertical levels. We can see the variability in values across both latitude and longitude, and also by level. This is shown in the range of values. Like in the subplots A at 1000 hectopascal, namely at the surface of Earth, there are low values in the Arctic and Antarctica, rising smoothly towards the equator. In subplot B at 500 hectopascal, we start seeing the turbulence of the atmosphere all around the globe. In subplot C at 100 hectopascal, some turbulence, but mostly near the equator. And finally, at subplot D, the highest level, we see that the variable is smooth, but just a portion of the Arctic. In this slide, we delve into the variation of key bits distribution among different vertical levels. In the left side, some illustrations to help understand what these vertical levels are like, assuming dry air at a constant temperature. So we have Mount Everest being at almost 9 kilometers at 300 hectopascal. Airplanes flying at 12 kilometers at approximately 200 hectopascals, and the atmospheric balloon at 40 kilometers at approximately 7 hectopascals. So the distribution of key bits varies depending on the level, with a prime example being the specific humidity variable in the purple color. However, it is important to note that this phenomenon does not hold true for all variables. Take, for instance, the temperature variable in the orange color, which have a consistent distribution across the various levels. So the bitwise, as a summary, the bitwise real information-based compression is executed as follows. First, we calculate the bitwise information and get the key bits. Secondly, we eliminate the bits lacking real information. And finally, we perform the lossless compression. Bit rounding the chunks before compression can enhance the compression by getting more details where needed without taking up more disk storage. And this is my last slide. Thank you for listening.